Welcome back. Last week we went over just overview of the course, and this week we will cover two lessons. One, which is today, projection, radiography, and computers in medical imaging. And then later this week we will learn about CT. Lesson 2, projection, radiography, computers in medical imaging. Okay, projection imaging. So projection radiography was actually what is invented back in 1895. We talked about this last lesson. And then radiography has evolved into one of the best imaging modality in terms of image quality and the resolution. Okay, so let's talk about this concept of projection imaging. Projection imaging is you project human body's 3D anatomy into 2D plane. Okay, so if you have a patient or subject, then you have X-ray source, and then you project it, and then you capture it in the 2D plane. Either this is film or like digital panel that we have in our department. All right, so let's define this term of transmission imaging before we move on. So transmission is not the opposite of projection. It's rather a different concept than emission or reflection. Okay, transmission imaging is basically your X-ray source is opposite side of your detection panel. Okay, but it is actually outside of patient body. Whereas emission imaging or reflection imaging, so let's talk about the emission. Emission is like nuclear medicine imaging. Your X-ray source is inside your patient, and then it gets emitted out. Then it is being captured. Okay, and then reflection imaging. We'll be talking about this later. But reflection imaging, it's not radiation. It's ultrasound, for example. The sound source is outside, and it goes in, and then it reflects back, and then gets detected. Okay, so it is reflection. So in projection radiography, as you see here, what do we have here is a chest X-ray here, and it is projection imaging and also transmission imaging. The X-ray source was outside of the patient body. So what does this film look like? So film, we call it screen film radiography. So film is actually made out of screen and film base and immersion. Okay, so it is typically sandwiched with both sides in the screen. Okay, and then this is plastic film base. Then we have these chemical layers of immersion. Okay, so what is screen? Screen is made out of scintillating material, means it absorbs X-rays and it emits visible light. So X-ray converted into visible light in this scintillating layer, and the film, rather actually immersion, detects this light coming from the screen. Okay, so what is made out of? It is made out of a high atomic number materials. Okay, why? To increase efficiency of stopping X-rays. So typical film imaging X-ray energy is typically typical 100 kilovoltage peak energy. So the high Z material of screen will be most effective to stop or interact in photoelectric effect. Okay, so the thicker the screens are, the more sensitive, but we cannot make the screen infinitely thicker because as screen gets thicker, it creates blurred image. Let's look at the next slide. So it's a short animation. Hopefully this will help you to understand. So the X-ray coming from the top, and then the screen converts basically X-ray into the visible light. I depicted in these yellow arrows, and that yellow visible light is captured by the immersion and film. So what is inside this immersion? Inside immersion, there's a silver halide crystals. They're suspended in this clear gelatin material. That's what we call emulsion. So as you all understand, the silver halide crystal is typically in the periodic table, these are halides, as you can see, and typically it is silver bromide or silver iodide. So some are actually combination of, typically 90-95% of silver bromide crystals and 5% of silver iodine crystals. They're actually suspended in this gelatin material. And there's also this by the way, these are actually some magnifying view of those crystals inside the gelatin. So this is actually the key component of this emulsion is these impurities. Okay, there are some defects within these lattice crystals, and these defects will help create latent image that I'm going to explain in next slide. So how does this image gets formed? So we call it latent image because during this image formation, you cannot really see the image. Okay, so you need further chemical process further down the road. So at first, we only have latent image. So there's a theory explained by Gurney and Mott. So here is the silver bromide crystal. And as you know, this bromide has abundant electrons. So some are loosely bound electrons in the silver halide, in this case silver bromide, will absorb light energy from the screen and it will drift as a free electron, as you can see in this image. These free electrons can reduce its energy and can become more stable by trapped by this, by trapping themselves by near the defects, impurities here. Okay, and then as more and more electrons being trapped near the defect, the silver ions, which is positively charged silver ions, will be attracted toward this defect, around this defect, and then it will form neutral silver metal atom. Okay, and then it'll be trapped here. Okay, so this is what we call latent image. So this is microscopic level, but you can imagine that if there is actually human body or hand or chest, you will where the radiation hits this silver bromide, you will get more higher density of these silver atoms will be formed as a latent image. Okay, once the film is irradiated and then latent images are formed within the film, then we'll have to feed that unprocessed film into this developer. Okay, the film processor rather. So it looks something like this. Looks like copy machine. So there's a dark room. You have to go inside a dark room, close the door behind you, and then open up the cassette of the film, and then you feed into this film processor. And then there's a bunch of rollers, and it goes through this chemical bath. Okay, so there's a developer and then fixer. So what does that do? I'm not going to detail, but it basically intensifies that silver atom. Okay, and then it makes the image more actually, the image contrast more stronger. And then it'll fix that silver atom onto the film base itself. And then all those unirradiated silver bromide will be washed away during this process, and then it'll be dried. So that's why the film will be a little wet and warm. So that was radiographic films, okay, which ironically we don't use it anymore. So what do we have in our department? We instead have radiochromic film. Okay, radiochromic film. Well, there is a reason why we made a transition to the radiochromic film. Okay, so while radiochromic film has a long history, it is started developed 1960s. But it is actually very recent actually improvement that made the use of radiochromic film actually more popular. So any disadvantage of radiographic film is, it is actually advantage of radiochromic film. So it is more tissue equivalent. So you remember, so what is it made what is the radiographic film made out of? It's a silver, okay, it's a high Z, so there's energy dependence. Whereas radiochromic film has a tissue equivalent material. There's no silver metal. And it is also insensitive to the visible light, not like radiographic film where you have to keep it in the cassette or keep it in the envelope, and then you have to develop in the darkroom. So radiochromic film, you don't have to do that. It is only sensitive to the actual radiation level of energy. And like I just mentioned, there's no need for chemical processing. So that's why we, in our department, we got rid of those image processor. Okay, so it is self-developing. I have some video I'm going to show you later. Then it is also has the same high resolution as the radiographic film. There are many different kinds of radiochromic films, but here I have an example of radiochromic EBT3 films. This particular film has this active layer of sensitive layer, very thin layer that is sandwiched between this polyester base. So this is the layer where when it interacts with radiation, it polymerizes and then it becomes darker. The color changes with the radiation. So I have actually video I'm going to show you next. All right, so this radiochromic film develops, it gets dark in real time. So this is actually just one thin strip of films that can be used during the HDR morning QA for source position checks. So we place this film under this jig, and it has this metal, let me grab my pointer. So it has this metal strip here. So when radiation source is coming out and it it emits radiation, the radiation bounces off this metal strip and it can form dark spots. So let me play this video in real time. Okay, so now you hear this beeping noise. That means radiation source is out. So if you look carefully, so it forms this shape, dark spot where the radiation is. And then it moves. We programmed it so that it can stay in multiple dwells, so at about 1 centimeter or 2 centimeter apart. Then it develops in the real time, as you can see. So this radiation is coming from the scatter radiation. So it forms the source position, and then it also leaves these marks from this metal strip. So that center of this spot, this circle, should be aligned with this strip. Okay, so that's how we do morning QA position check. So it is very handy because you can literally check in real time. And then there's no film developer, there's no darkroom, so it is very handy. And we do this every day when there is actually procedure. Okay, so that's how it can be used. Very, 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 very convenient. So the films, when it is irradiated, depending on what you irradiate, will have degree of darkness. So in this example, I have this wedge, and then the X-ray is coming down from the top. So when you place film, the amount of radiation that is going through will be different. That will create these shades of darkness. So the less attenuation here on your right side will create darker radiographic image. And on your left, because radiation is going through this longer path, like more amount of attenuation, so the less amount of X-ray will reach to the film. That'll make film brighter. So we want to quantify this degree of shade by introducing this term optical density. So optical density is the degree of darkness. So let's define mathematically in next slide. So optical density is mathematically defined as negative log of 10 of transmission. So in other words, it's log 10 of 1 over transmission. So what is transmission? Transmission is the ratio between the incident intensity of the X-ray and then what is coming out the other side. So for example, when transmission is 0.1, like say 10% of the X-ray is reaching to the film, then the optical density will be, just plug 0.1 here, and then optical density will be 1. And the transmission of 1%, 0.01, that will create optical density of 2, so it gets more darker. So what about if the film is perfectly clear and then there's no radiation, then what would be your optical density? So perfectly clear film means your transmission will be 100%. So that is 1, right? So what is log of 1 over 1? So that is log of 1, and which is 0. So your optical density will be 0 if it's perfectly clear film. But in reality, the unexposed film has inherent darkness, either coming from the film has inherent film tint that we deliberately introduce, and the fog. The fog is developed by this background radiation. So depending on how the films are kept, the fog will develop because the natural radiation is everywhere. So the fog and base has to be typically less than 0.2 optical density to be used clinically. So this figure here is showing the densitometer. So you place the film and then you place this probe down, and then it can calculate optical density for you. So here we are plotting radiation exposure, so basically amount of radiation, and then y-axis is optical density. So the more the radiation is, the darker the image the film gets. So you will typically have some relationship like this, and then each film has its own inherent characteristic. So Hodder and Drifel curve, HND curve, also known as characteristic curve, is log-log plot, because optical density itself is log. We call it log-log plot. Okay. So here you see, without even any radiation, you will have some optical density that we defined as base plus fog. Then you have tau, and then this linear region where you can correlate the exposure and optical density, and then it will saturate after a certain amount of radiation. So in other words, if you know the optical density, if you measure optical density, you can correlate that into the amount of radiation. So I just mentioned that it is film specific characteristic. So here we're comparing two film A and film B. They're actually designed differently. So which film is more sensitive? So you can actually see in different ways. So for example, for the given optical density, this film A requires significantly less amount of radiation to achieve the same darkness. Okay. So let's look at another example. In this example, you have a film A and film B. So you can say that film A is very sensitive and film B is less sensitive than film A. So for a given exposure of say 3 MR, the film A is already saturated, right? Whereas film B still has some room to go even darker. Okay, so film A has a narrower latitude than film B. So latitude can be defined as the sensitive radiation, sensitive exposure range rather. Okay, so film A has very compared to film B, has a narrower latitude. So the resolution of film A, they can resolve the radiation is very narrow. So it can be only useful for exposure of 0.3 to up to 1 MR here. Okay, but it's sensitive, so you don't need much radiation to irradiate film A. So what I'm trying to say is each film has its own characteristic. So as a physicist, you have to decide what type of film you want to use for film QA, or depending on what type of QA you're performing, you have to choose right film. So that was about the films. So we talked about radiographic film and radiochromic film. Let's talk about another class of radiography tools. So it's called computed radiography, CR. Okay. So here you'll have a picture. We have a picture of the CR plate. So this is not a film. It is actually it's a phosphor stimulable, photostimulable phosphor detector system, PSB detector system. So what happened is you use this plate in place of film. So when X-rays are absorbed by this PSB, much of the X-ray energies are trapped, and then it can be read out later. Okay, it can be stored in days. So this is like cassette. Okay, so how does it get read? We use laser light to stimulate the emission of this trapped energy. The trapped energy will be stimulated by this laser light. Then it can be collected. The visible light will be collected using this photomultiplier tube, PMT. Okay, and then it can be reusable. So not like films, the plate, the CR plate, can be erased by scanning with a bright white light. So in place of film, you place this CR plate here. Then the procedure is very similar, right? So you play X-ray and you irradiate the patient or object. Then CR plate will store that information. Then you hand carry this CR plate to the digitizer, and then you get the digital image from that CR plate. So this is actually what reader looks like. So you would place this. You feed the CR plate in, and then inside this reader, digitizer, so your CR cassettes going in, and then you have this laser light scanning through, and then the stimulated trapped energy will be read line by line, and then it'll be collected by photomultiplier tube, and then analog to digital converter, and then you get 100% digital image, and then it'll be erased by bright light, and it can be reused. So whereas a screen film has narrow dynamic range where you can use, in other words, the window that you can use to create good image, the CR computer radiography has this very, very wide dynamic range, which is significant advantage over the conventional film. Okay, so this usable optical density is very, very wide. So well, this is a good thing, or if you're not careful, actually you end up irradiating more, because at first when this was introduced, therapists actually figured, okay, it doesn't really matter how much exposure, you still get good image. So if you're not careful, actually you end up using higher dose. So this is advantage, but we have to be careful at the same time. Here I'm introducing direct capture digital radiography, like DR, okay, which resembles more like what we have in our department, like OBI, kilovoltage imager or MB imager. It's not like a CR plate where you have to carry it around and feed into the reader. Okay, this DR is like stationary or like attached to the machine, and then it basically reads the data directly from the imager to the computer. Okay, you don't have to take it off and feed it into the reader. Okay, So there are two different types of digital radiography. So one is, as you can see on your left, is indirect, and then on your right is direct. Okay, so AMFPI stands for active matrix flat panel imager. So it's active matrix flat panel imager. Okay, active matrix flat panel imager. So on your left, let me erase this. So is indirect. So what is indirect? So radiation, X-ray coming down, and then this layer is phosphor, such as a cesium iodide. Okay, so what happened is that X-rays is phosphor, so it converts X-ray energy into visible light. Okay, and then this photodiode will collect the charge from the visible light, and it'll store locally. Okay, the charge will be stored in locally, and then it will be read later. Okay, so it is because it is active matrix flat panel, so depending on the size of each matrix or each pixel, you get digital image for each pixel. Okay, on your right is a direct AMFPI. So what is direct about it? So it is in a direct DR uses semiconductor material, so layered between two electrodes. So we have two electrodes here. Sorry. And then the charge is actually collected directly from the X-ray. Okay, so this charge, because there's bias applied, and then the charge, negative charge will go up, and positive charge will go down, and then it'll be stored locally again. Okay, so there's no conversion between like X-ray and visible light. The X-ray itself is collected directly. Okay, so it has a great advantage in terms of image resolution, because there's no lateral drifting or like spreading. So the direct DR has great resolution. Okay, so this is actually more like what we have in our department, like OBI, kilovoltage panel and the megavoltage panel. Okay, so you don't have to take the panel out, right? The electronics are connected directly, and then the image, when it's irradiated, almost instantaneously we acquire image. So let's talk about a digital image. Okay, so what do you see here? Okay, what do you see here? It looks like what kind of image modality image is this? Is this MRI? Is this PET? No, these are CT image of like torso area. Okay, unfortunately this patient has something going on the patient right hand side, so so we can appreciate what dark area is, like a low density lung, and outside the patient is air, and you can also appreciate there is actually bone, and that there's fat and muscle. Okay, but let's zoom in a little bit what's going on. So if you zoom in this rib area, you can start seeing, okay, these are actually pixels. Okay, so if you zoom in further, each square has its own uniform grayscale. Okay, and then it is actually, the image is made out of a bunch of this uniform grayscale pixels. Okay, so each image has these numbers, okay, pixel size, and at the CT image, as you saw before, depending on what technique was used, so slice thickness can be assigned, right? So this becomes a pixel size XY, and then Z. So this will become a voxel. Okay. So what's voxel? Voxel is a volume element. Okay. So like I said, voxel size is pixel size XY times slice thickness. So if we have image, okay, covering 25 cm by 25 cm area, and we use array size of 512, then what would be the pixel size? Okay, pixel size will be about half a millimeter. Okay, this is typical CT image. So let me draw something. So say typically CT slice is square. Then you have some object. Okay, say this is some 20 cm. Okay, and then the whole from left to right is say 25 cm. Okay, and then it is covered by 512 pixels by 512 pixels. Okay, so there is basically 512 of these. Okay, then each pixel size will be less than a millimeter. Okay. All right. So now, if we assign the slice thickness, if we ask CT's machine, okay, I want to give. Okay, so another way. So say if we have in the coronal view, okay, so this is actually patient, and say from here to here is 15 cm, okay, and I want to have this 30 different slices, okay, and then that is typically 5, maybe not typically, it's 5 millimeter slice thickness, but actually in reality, in practice, you tell CT scanner, okay, I want 5 millimeter slice thickness, I want 1 millimeter slice thickness, and so forth. Then the CT machine will generate, depending on your slice thickness assignment, will have multiple slices. Okay, so, and I just want you to actually understand, okay, pixel size, how it is defined, and then the relationship between slice thickness and then number of CT image itself. Okay, I mean it can be CT or it can be MRI, but digitally. Okay, what is slice thickness versus the physical object size? Okay, so this 3D image volume, it can be anatomy like we just saw from CT, MRI, or it can be actually dose. Okay, it can be in three-dimensional dose. Okay, so each voxel will have some information, either anatomical information or radiation dose. Okay. So how does this information get stored inside the computer? So we have to talk about a little bit of math, but hopefully it's not that complicated for you guys. So for example, this is our numbers, right? Base of 10. So to express 173, we break that down into, we have a 100, which is 1 times 10 to the 2, and 70, which is 7 times 10 to the 1, plus 3, which is 10 to the 0. So everything is base of 10, right? So 10. But in computer world, the numbers are either on and off, right? It's either 0 or 1. So the same number of 173 is stored as 10101101. So, as you can kind of follow this example here, the first one stands for 1 times 2 to the 7, and second is 0 times 2 to the 6. So 7, 6, 5, 4, 3, 2, 1, and 0, and so forth. To save 173, you need 1, 2, 3, 4, 5, 6, 7, 8, basically room. Okay, so you guys maybe already know about this. This is a base of 2 in digital world. Okay, so like I just mentioned, to save the information of 173, you need this 1, 2, 3, 4, 5, 6, 7, 8 bit. So each entry here is called a bit, is binary digit. Okay, so either 0 or 1. So each bit can be a on or off. Okay, so if you have 8 bits, that can be a 1 byte. Okay, maybe you guys are familiar with this term byte. Okay, so this 8 bits of space, the maximum number you can store is 255. So it's basically 1 times 2 to the 8, 2 to the 7, 2 to the 6, and so forth, 2 to the 0. The smallest number you can save is obviously when everything is 0, it is 0. So 8-bit storage can store the maximum of 255. Okay, so one way of figure that out is what is the maximum number that it can store? You can say the 2 to the number of bits minus 1. So if for the 8 bits image, the maximum number it can store is 2 to the 8, which is 126 minus 1. So 255. So that was 8 bits. So what about 16 bits? So what is the maximum number that can be stored in 16 bits? So in same fashion, so you do the 2 to the 16 minus 1. So it's about 65,000. Okay, so when everything is 1 in this 16 bits, the highest number it can store is 65,000. Okay, so in medical imaging, most data is represented using this 16 bits or 2 byte. Okay, so 1 byte is 8 bits, so 16 byte is 2 byte. Okay, so actual CT image itself has typically 12-bit depth. Okay, I'm going to explain what depth is later. But it also takes up the same memory space with 16-bit image. Okay, so 1 pixel of CT you can count as it requires 16 bits of image. So going back to my original CT image example of the torso, let's try to estimate the file size of this 1 slice CT. Okay, so typically CT image, 1 slice CT image is composed of 512 pixels and then 512 pixels across. Okay, so the total number of pixels in 1 slice will be 512 by 512, and each pixel or voxel, depending on how you define the thickness, has 2 bytes, okay, of information stored. Okay, because each pixel we have grayscale number. Okay, so I mentioned that it is typically 2 to the 12 for CT, but there are some modern CT scanner that it stores 2 to the 16 pixel depth. But say the conventionally it is 2 to the 12. So the grayscale of CT image 1 pixel can range about 4,000. Okay, so it can be really as dark as black and as bright as white, and in between you can have a pixel, we call it depth, or you can say it as a shade, grayscale shade of 4,000. Okay, but it can be 16-bit too. It can be, then it'll be like 65 K. Okay, but anyway, so let's, regardless, okay, either 16-bit or 12-bit, you need 2 bytes of space. Okay, so I explained that previous slide. So for this 1 slice of CT is 512 by 512 by each one requires 2 bytes of storage. So that is this much a byte. So how do you convert bytes into kilobytes or megabytes? It is actually, it's not just 1,000. Okay, 1 kilobyte is 2 to the 10 bytes. Okay, so it is important that you understand this. And then 1 megabyte is 2 to the 10 times 2 to the 10 bytes. So 1 megabyte is not 1 million bytes, it's rather 1,048,576 bytes. Okay, so you can easily convert this into this. So at the end of the day, 1 CT slice is about half a megabyte. And now if you have 30 slices, okay, total, then all you have to do is just multiply the size of each slice times number of slices. Okay, so that'll be say if you have a 30 slices, that will make about 15 megabytes. Okay, that's how big of data is for CT. So to help you understand the shade, the depth of shades, let's look at this example one more time. So in this example, this image, okay, total shades, okay, total number of shades in this picture is 4. Okay, so dark, okay, dark here. Let me use my pointer. Dark, black, and white, and then 2 different grayscale in between. Okay, so that's 2-bit depth or 2-bit image. Okay, so 2-bit is, just remember 2-bit is, that means that there are 2 space, okay, to store image. Okay, so what is the brightest, what is the smallest number you can save? Okay, 0, 0. Okay, and what is next shade? Next shade will be 0, 1. Okay, then the other will be 1, 0, and then last one will be 1, 1. Okay, so in other words, it's a 0, 1, 2, 3. Okay, so there are 4 different shades in this image. So that's how 2-bit image look like. But let's increase our depth range. So this is 4 bits. Okay, so by making the room of 4 bits, okay, so you have 16 shades of gray. So 2 to the 4 rather. Okay, 2 to the 4. The total of 16 shades of gray. Okay, so as you increase the bits, okay, in this example, it's 8 bits, 256 of gray shades. You can really, appreciate, okay, this is much better image than the previous examples. So these are typical image size for different medical imaging modality. Okay, so we talked about CT, which is 512 by 512 typically, and 8-bit depth of 12 bit. Okay, but there are some more advanced mode in CT, 1024 by 1024, which we use in our department for head and neck, and then it can be a 16-bit depth. Okay, so whereas the PET, the nuclear medicine imaging, has only 128 by 128. Okay, so it's a poor image resolution. So we'll learn later on why that is. But typically is either 12-bit or up to 16-bit depth of images available. Okay, so let's move on. So even though the medical image has 12-bit, 16-bit, like thousands of shades, but your computer display, okay, your typical monitor can only differentiate 256 depth typically. Okay, so how do you visualize this, very high thousands of shade image on your monitor if your monitor can only display 256 depth? Okay, so here comes window and leveling. Okay, so you guys are all familiar with this concept of window leveling. So let's look at this. The original image depth range is about 4,000 in typical CT image. Okay, but your computer can display only 0 to 255. Okay, so you can make your window size, okay, and level depending on what you want to see better. Okay, so in this example, we are actually selected from here to there. I want to project to my monitor. So now the shade from here, from here to there is now becomes the darkest. This part will become the darkest, and this part will be the brightest on your computer. Okay, so that's how we change window. And then level means where is the center of that. Okay. So I have an example here. Next slide. So, well, before I go to the example, so typical CT image is something like this. Okay, so it can be as dark as CT number -1000 air. Then by definition, the water will be 0. We'll learn about this later. And then bone can be as high as 1000 and even higher for the cortical bones. Okay, so CT has this range. Okay, this is only showing about 2000, but in reality, CT image has about 4000 range. Okay, so we picked soft tissue window in this example. So we know that soft tissue mostly resides in this range. Then we display this point as black and this point as pure white. Okay, this is what you see here. Okay, you can appreciate the soft tissue, fat, and but all the bones and high density here is saturated as white. Okay, let's look at another example. So this time it is a long window. You're all familiar with the long window. Okay, so long window we expand. Okay, I want to include all the air, and I'm not interested in up here. So again, everything here will be saturated. That's why it's all bright. You can't really tell the bone in long window, but you now have much better differentiation in the lung nodules and these blood vessels within the lung in this long window. So now we are looking at from here to there, okay, and divided into 256. Okay, so last example is bone window. So you see you can, okay, like not like the other two examples, like bone, you can see inside even within the bone because we set our window to the area with a high CT number. Okay, so everything here, like you can't really see the lung and air because it's all dark because we set our window from here to there. Okay, so now you appreciate much better the bone. All right, so we covered a lot today. So we, talked about radiographic film, how the latent image later develops into actually image, in molecular level, atomic level. Then we talked about radiochromic film that instantly develops. You don't need a dark room. And then we talked about how we can quantify the darkness of the film, optical density. Then we briefly talked about different characteristics of certain films. Okay, some films doesn't require as much radiation exposure to develop certain darkness. And then we talked about CR, computer radiography, how it can be read, how we can store image. And then modern imager, direct or like a digital radiographic imaging. Just like what we have in our department, like OBI panels. Okay, so there are two different types of DR, direct and indirect, depending on how we create this digital image. And then we attempted to compute the file size of the computer medical imaging. And then now we all know what's the difference between 12-bit, 16-bit, and so forth. And we all learned today that one CT slice typically is about 0.5 megabytes. Okay, and we concluded today by showing the window and leveling. Okay, so even though your computer can only show 256 different shades, by applying different window and level, we can actually visualize what we want to see depending on the application. Okay, there was a bone window and soft tissue window and so forth. All right, so I hope you guys find this interesting today, and let's see you next week or next lecture. Bye.